you.
So for our first talk of the morning, welcome back everybody. For our first talk of the morning, we're happy to have Hans-Peter Nilles telling us about unification of flavor, CP, and modular symmetries.
Okay, thank you very much for the invitation and giving me the opportunity to be here. I'll talk about flavor physics essentially, and this is. Can you hear me? Can you hear me?
Yes, we can hear you.
Okay. Flavor symmetry, in the hope that this is an issue where we can, in a certain way, connect on one hand string theory and on the other hand particle physics, because the question of flavor is an interesting problem in particle physics. So the outline is we will discuss the world of flavor from a top-down point of view, as it can be derived from string theory. It relies heavily on the Narine lattice formulation for torus compactification, and in fact, the Narine space group of a twisted lattice. The discrete flavor symmetries can be identified as the outer automorphisms of the Narine space group. They include various components like traditional flavor symmetries, which we know already, modular flavor symmetries, and they also contain a natural candidate for CP symmetry. And they in fact give you a unified picture of discrete flavor symmetries. This leads us to the concept of an eclectic flavor group. It combines the different flavor symmetries in a bigger group. And that's the maximum group of flavor for a given model. In particular, it's interesting to look at the discrete symmetries beyond traditional flavor symmetries, which are built on the modular or syncretic groups, which in our case will be SL2Z and SP4Z. They appear in compactifications that exhibit elliptic fibrations. And the whole picture leads to a unified group of quark and lepton flavor. And in fact, the concept of localized flavor groups, which I'll discuss a bit later. So most of the parameters of the standard model of particle physics contain flavor. So these are the masses and mixing angles of quarks and leptons. And there's no real theory for that. There are many fits from a bottom-up perspective with discrete symmetries. So here are some of the groups which has been chosen, like S3, S4, A5, delta 27, delta 54, etc. And they seem to be quite successful. One aspect of flavor symmetry is the fact that quarks and lepton sectors seem to require different models for flavor. We have small mixing angles in the quark sector. The mixing angles are all small, whereas in the lepton sector, we have some large mixing angles between the different species. In addition, of course, flavor symmetries are spontaneously broken, and they require the interaction of so-called flavon fields that lead to a spontaneous breakdown of the flavor symmetries. Now, there are many bottom-up models which are successful, maybe too many. And they, of course, are based on various choices of the group above and also the representation which has been chosen. But there is not a single group or representation which is singled out. And we are still missing a top-down explanation of flavor. And so in a certain way, it is important to have a top-down explanation as well. So flavor symmetries in string theory, they can come from specific string theory selection rules, and also from the symmetries of the compact extra dimensions. As an illustration, we consider orbifold compactifications of the heterotic string because they provide models with a chiral spectrum of quarks and leptons with the gauge group of the standard model. So at least that allows us to define flavor. We need quarks and leptons. And we will see that their abundant discrete symmetries are candidates for flavor symmetries. And one idea would be that at a given point, one might make connection to bottom-up constructions of flavor. So a summary of the predictions of the string theory will be given here so that you will find your way through the latter part of my talk. There will be traditional flavor symmetries, which are the ones which we had discussed a lot in the last decades. They are universal in moduli space. In addition, there are modular flavor symmetries, NCP, that are non-universal in moduli space. So that's the difference. So traditional flavor symmetries will be defined in the way that they're universal in moduli space. But these symmetries, they will unify to the eclectic picture of the flavor symmetry. And one important thing is that you cannot just have the one without the other. In a lot of bottom-up constructions, people use now modular flavor symmetries. But if you have them, you will also have traditional flavor symmetries, and you have to take that into account because that gives important restrictions for your theory. Now, the non-universality in moduli space is very interesting because it needs to what we call a local flavor unification at specific points in moduli space. And it will then allow a potentially different picture for quarks and leptons. It will also allow a spontaneous breakdown of the flavor NCP as a motion in moduli space. If you are at the specific points, you have an enhanced symmetry, but if you go away from it, it will be the enhanced symmetries will be spontaneously broken. So let me give you a simple example how you can get flavor symmetries from strings. I consider the T2 over Z3 orbifold. So we have a lattice vectors E1, E2. They have the same length, and there's an angle of 120 degrees between them. We orbifold out this 120-degree rotation. That will lead to this object, which is in the dark shaded region. There are three fixed points, X, Y, and Z with it. And the Z3 orbifold is the one where you take this fixed point is the same as X. You take this one, flip it over, and glue it at the edges. That's the Z3 orbifold. So we have these fixed points, and at the fixed points, we can have twisted fields, which are located at these fixed points. So for example, in this case, we'll get a discrete symmetry delta 54. We have the twisted fields, and we have an S3 symmetry from the interchange of the fixed points, the three fixed points. And from the orbifold selection rules, we have a Z3 times Z3 symmetry. The multiplicative closure of these groups will lead to delta 54. Delta 54 is a non-abelian subgroup of SU3 flavor. It has 54 elements, and it could serve as a flavor symmetry for three families of quarks and leptons. And in this case, it is that the quarks could be triplets of delta 54. But of course, this is now, we have seen in a simple system, we have already a rather large group with 54 elements, and we have to ask the question, is there some general construction which allows us to deduce the flavor symmetries of the theory, especially since we could be confronted with more difficult situations. And in fact, the general mechanism in this case to find a complete set of flavor symmetries is based on the outer automorphisms of the Narayan space group. So let me shortly discuss the Narayan lattice. When in string theory, we have, for a d-dimensional space, we have d left and d right, left and right moving degrees of freedom. So y, the coordinates given from yr and yl, you see on the lattice are identified with a lattice shift vector, where E is the Narayan field-bound matrix, which depends on the moduli of the theory. These are the radii, the antisymmetric tensor fields, the angles. And N and M are numbers. They are the winding numbers and the Kaluza-Klein quantum numbers of the theory. So in fact, we do not have, when we now compactify here on that lattice, we do not only have Kaluza-Klein quantum numbers, but we also have winding numbers for the strings, where the string can wind around the compact dimension. Now, so now we can take the Narayan lattice. We divide by, let's say, a ZK orbifold twist, which looks like that. We take a simple case. So theta or capital K is equal to 1. So for the Z3 case, K will be 3. Theta L and R are now elements of SO2D. And we choose a symmetric orbifold, which has theta L equal to theta R for simplicity. And we also do not include off-diagonal elements, which would correspond to so-called rotor translation. The Narayan space group is then given by theta to the k, by the twists and the shifts. And the outer automorphisms of that group map the group to itself, but they are not elements of the group. Of course, they include also modular transformations, because we have seen that we have Kaluza-Klein quantum numbers here, as well as winding quantum numbers. And so we'll get modular symmetries appearing. So there is, this is the generalization, this is the manifestation of T-duality in string theory. While for this audience, I don't have to explain that. One has momentum exchanging winding and 1 over R, and then you have this T-duality. You map one theory to its T-dual. Now, of course, when the string scale is large and the low energy effective theory is just described by momentum states and winding states are heavy. So one could ask the question, can T-duality play a relevant role for flavor symmetry? And in fact, you will see, yes, it can. And that goes through the modular discrete symmetries which exist in the theory. So now let's generalize to 2 dimensions where we have the modular transformation of SL2Z, the Möbius transformation. Of course, they are acting on the Kähler and the complex structure moduli of the torus. The group SL2Z is generated by the 2 elements S and T, with these properties where S interchanges the modulus. So this is the T-duality transformation discussed earlier. So the modulus goes to -1 over M, and T is a shift in the moduli. Further transformations which appear here is a symmetry which transforms M to -M bar. This will be very important and will be the natural candidate for CP. For the CP symmetry. In addition, we will have a mirror symmetry between the Kähler and the complex structure moduli. So this is the fundamental domain. So you look at the upper half plane of M, and the dark shaded region is the fundamental domain of SL2Z. So everything can be described here in that fundamental domain. So we come then to the modular forms. The string dualities give constraints because it's a symmetry in some cases. So when we have the modular group SL2Z, it transforms a modulus in this way, where AD minus BC equal to 1 with integers. And the matter fields transform as modular weights, modular functions of a given weight K. So if rho is a representation of this group acting on phi, you will not only have that representation acting on phi on, let's say, a matter field, but you will also have a so-called automorphy factor with a given modular weight K, which is important for the theory and the properties of the theory. So we will have first the group, its representation, but we will also have these automorphy factors in the final form. So let's now see what that means for the orbifold T2 over Z3. Again, we have a situation here that we have E1, the length of E1 is equal to E2, and the angle is 120 degrees. So some of the moduli, of course, are frozen. And so the complex structure modulo now is frozen because of this property. And the modular transformation, which we get for the Kähler modulus T, now they transform as a subgroup of SL2Z. And so then so the step now is to go to define gamma free, which is a mod 3 subgroup of SL2Z, where you allow for Z modulo 3 transformations. And then when you take, so this is still an infinite dimensional group. Then when you divide SL2Z by this subgroup, then you will get this gamma free, which is called the discrete modular flavor group. So gamma free is actually coincides with A4, which is the even permutations of 4 objects. So that's just a fact. It's an automorphism. Gamma free is A4. But in fact, here we have to deal with the double cover of T prime of A4 because the twisted fields act non-trivially. So this gamma-3 will act on the moduli as A4, but if it acts on the non-trivial, on the twisted field, it acts as T prime. So that's like when you look at the spin, if you have O3 with the cover group of SU2, if you have half integer spin. In addition, we will have a CP transformation, which is M going to minus M bar. And that will lead to the full discrete modular group here, which is GL2,3, which is 48,29 in the gap notation. So this is a notation according to the gap program, which classifies groups. The first entry here is always the number of the elements of the group, and the second one is a number which shows the classification in this program. So that is what we get here. So the flavor symmetries, now we will have these the traditional flavor symmetries as we had before, delta 54, and we also have the flavor group, the modular group T prime, which we have here. But of course, these full flavor symmetry is non-universal in moduli space, so it is not usually linearly realized, the group T prime, and so we will have a hybrid picture of these symmetries. So here we have, as said, the traditional flavor group. It's universal in moduli space. It's universal in moduli space, and and there's the modular flavor group, which is T prime. The eclectic Fruver grape is defined as the closure of these groups. So here we obtain a group omega 1, which has 648 elements. And if we include CP, we actually get a group which has 1296 elements. So modular flavor symmetries have been discussed recently by Ferruglio in a bottom-up picture. He actually shows the discrete modular group gamma-3, which we said is isomorphic to A4. By now, there are many more constructions based on this, from gamma n with higher n and all kinds of possibilities. What is important to see is in a bottom-up model building, you choose the group, you choose the representation, and also you choose the values of the modular weights of the matter fields. But here we would now confront that to a top-down construction. If we have the modular flavor symmetries, of course, we need flavon fields. The flavon fields to break the group are given by the moduli, at least part of them. The modular flavor group is given by the string theory. But the string theory also tells you the representation and also the modular weights which appear. And in fact, depending on the modular weights, you will have further symmetries, an enhancement to further symmetries. And the discrete group which we have here is always accompanied by a traditional flavor group. And that, of course, further restricts the couplings, Kähler and superpotential. So there's now something when you compare top-down to bottom-up, there is what I call the representation dilemma. So for example, in this bottom-up, you typically take a triplet of A4, and you have the non-trivial singlet representation for the various quarks or leptons for left and right-handed sector. And there's, of course, a complete freedom to choose the modular weights. Now, when you try to do such a model, the top-down approach, the best we could get up to now is not that we have A4, but we have T prime, which the double gamma of gamma-3. But gamma-3 is not a subgroup of T prime. And the twisted field does not transform as a triplet of this group, but as a 2' plus 1 transformation. It's also very difficult to get all these non-trivial singlets in the low energy sector of a string theory. In addition, the modular weights are restricted in this model, which we discussed here, to -2/3 and -5/3, and they cannot be chosen arbitrarily. So that means that the bottom-up, many of the bottom-up constructions use that decrease of freedom, and it's a question to see whether that can be embedded into string theory. And this seems to be difficult. So where are we at this point? So far, we have discussed the two-dimensional set 3 orbifold with the Kähler modulus. Of course, we in general have the complex structure modulus U as well, if we just have this torus. So this.
You have about 5 minutes left now.
Okay, thank you. This leads to the product of these two groups. In the set tree case, U is frozen, but still, even if it is frozen, it contributes with an additional flavor which additional R symmetries to the flavors, and this comes from these automorphy factors. So what we get here is that we get then actually a group which has 1944 elements without CP. In the set 2 case, we have both types of moduli, and they actually give an eclectic group with 2,304 elements. The next step would be, has been done already, I will not talk about that, we'll consider the Siegel modular group SP4Z, which includes a Wilson line in this scenario. So this will be done recently. I also mentioned the talk of Anna Maria Font earlier this week, where she discussed this connection in some way. Now, next step I want to discuss is local flavor unification. We had the fundamental domain of SA2Z. Now we get the fundamental domain of gamma free, which is this whole shaded area. In fact, when we include M going to minus MM bar, we can divide it to a smaller region. So we have here the S transformation, which transforms the modular to minus 1 over M, T to M plus 1, and U to M minus M bar. And now we see this moduli space, and at certain points in the moduli space, which we have enhanced symmetries. For example, this is a fixed point of S. These lines is a fixed point of TU. You have fixed points where two lines meet. In fact, these red lines here are usually the regions where CP is unbroken. And if you move a bit away from that, you will have broken CP. So you will have enhanced flavor groups at certain points in moduli space, and they will be given here. For the model we discussed, there's delta 54. This is universal in moduli space, but if you have on the lines, you have a group which is twice as big. When two lines meet, you have a group with 216 elements, and when three lines meet, you have a group with 324 elements. So you have bigger flavor groups, enhanced flavor groups at different points in moduli space. For the set 3 orbifold, we have a similar picture. So this will look in a situation like that without explaining very much the details. What you would see here, there's this line which also shows that here we have the mirror transformation which exchanges T and U moduli, which in fact in this symplectic picture with the Siegel modular forms will become a symmetry of the theory. So let me come to the messages which I wanted to convey here. The top-down approach to flavor symmetries, it leads to a unification of various discrete flavor symmetries as well as CP. We should stress again that modular flavor symmetry is actually a prediction of string theory. This is, of course, known since 30 years already, but in some way it has been forgotten in between, at least when we try to apply it for particle physics. There's a traditional flavor symmetries with universal in moduli space. There are non-universal enhancements, including CP as some basis. And CP is a natural consequence of the symmetries of the string theory. Potential flavor groups are large and non-universal. They are, of course, spontaneously broken. And some of the breakdown is in a certain way a motion in moduli space. If you go away from the special points of line of enhanced symmetry, these symmetries are spontaneously broken. So this in sum opens up a new arena for flavor model building, also to make connections to the bottom-up constructions. Up to now, of course, explicit string constructions are very rare. There have been some constructions from these people some years ago where they explicitly constructed set 3 cos set 3 orbifolds, which actually have sectors which have delta 4 symmetries and also the T prime symmetries. So we have seen that there is this concept of local flavor symmetries, and that in a certain way gives the hope to explain the different structures of quarks and leptons in the same theory. It's just that you have to go to different locations in moduli space to realize that. But we have, of course, to be careful in model constructions in the bottom up, in the sense that it's not all the possible representations appear in the massless sector. They all appear, but some of them are heavy. For example, the doublets of T prime in some way, the doublets of delta 54 typically are winding states. So there is still a huge gap between the top down and bottom up, but there are strong restrictions from the modular symmetries, the representations, and the weights. So this and me here, the summaries you can read by yourself. Thank you very much.
Okay, thank you, Hans-Peter. Let's all thank him for the nice talk. Yeah, so you can raise your hand or post something in the chat if you have questions. We already have one question from Dieter Lust.
Yes, thank you very much, Hans-Peter, for the nice talk. I would have like the following. If you consider these flavor symmetries in the EFT, the effective field theory, I would assume that they are discrete gauge symmetries, right?
Yeah. Yeah.
So are they always embedded in some continuous gauge symmetry? Do you know this?
No, well, partially they are. In some cases, actually, you can see that when you go to certain locations in moduli space, that you get an enhancement of continuous continuous gauge symmetries. But I don't think that is always the case, because you do some non-trivial twists, and in that respect, I think there is these, some of them are really. I could be understood as discrete.
But you would agree that this is a discrete gauge symmetry, in order
that's by definition is a discrete gauge symmetry, because you have all the representation somewhere in the string theory. So from that point of view, it's not that you have all the Wilson lines and all these things there which come with a gauge symmetry.
Maybe it would be interesting to see if it's always embedded into a continuous group, or whether it's not the case.
Yeah, no, that's something. Yeah, one has to think about that. Yeah.
Thank you.
Okay, so we can move on to our next question, which is from Fernando.
Yeah. Thank you, Peter, for the nice talk. Just for this audience, or for myself, could you tell us this use of modular symmetries in phenomenology? What is it that motivated them, and what is it that they have achieved?
Well, the point is that you see, I guess it's really Ferruglio who initiated that a few years ago. We could have done that 30 years ago, but where we had T prime already. But I guess we were too far away from this. The point, of course, which he made in some way, that it's more restrictive because you don't need flavon fields. You see, if you have a modular symmetry, the modulus breaks the symmetry. Whereas in all these others, you have to invent new fields, which are so-called flavon fields. They need to get left to break the symmetry. Whereas here, in this picture, you don't need flavons. The moduli which are there itself, they do it. And in fact, you see, they lead to models where in some way, when you want to fit the data correctly, very often you are very close to these fixed points in moduli space. Yeah, because if you are close to the fixed point, you get small numbers. And you know that when you want to describe flavors at some points, you have to get hierarchies from small numbers. And of course, this is also interesting from the point of view that sometimes when you look at the question of moduli stabilization, which I have not discussed here at all, which hasn't been discussed yet very much, very often you are driven to points which are close to these fixed points. So from that point of view, I think that was the major point. And in fact, so from the point of view compared to all the other constructions up to that, let's say based on the group A4, you could fit the leptons with less free parameters than other people did that. But still, he had this, he could choose these peculiar things like a triplet, non-trivial singlets here for the second and third generations. And also there was pretty much a choice for the modular weights, which was very important in that fit.
Okay, thank you.
Okay, thanks. Let's all thank Hans-Peter again. And we can move on to the second talk of the